Hello and welcome back. In the previous course, we have seen this diagram which tells us that by adding resistance and reactance together as vectors, we get as a result the total impedance. But what exactly is this reactance? And what is XL or XC? Let's find out. So, reactance is a measure of the opposition of capacitance and inductance to current. It acts almost like resistance, so the higher the reactance, the stronger we'll try that particular circuit or component to reduce the current. Reactance varies with the frequency of the electrical signal, and it is also measured in ohms. There are two types of reactance that you have to keep in mind. The first one is capacitive reactance and inductive reactance. The total reactance is the difference between the two. Now let's discuss each one separately, and the first one will be capacitive reactance. In an RC network tutorial, we saw that when a DC voltage is applied to a capacitor, the capacitor itself draws a charging current from the supply and charges up to a value equal to the applied voltage. Likewise, when the supply voltage is reduced, the charge stored in the capacitor also reduces and the capacitor discharges. But in an AC circuit in which the applied voltage signal is continually changing from a positive to a negative polarity at a rate determined by the frequency of the supply, as in the case of a sine wave voltage, for example, the capacitor is either being charged or discharged on a continuous basis at a rate determined by the supply frequency. So, as the capacitor charges and discharges, a current flows through it which is restricted by the internal impedance of the capacitor. And this internal impedance is commonly known as capacitive reactance. If you have a capacitor and you want to calculate its capacitive reactance, you can use this formula here, where F is the frequency of the signal passing through the capacitor, C is the capacitance in farads. As you can see, capacitive reactance varies with the frequency, so capacitive reactance is large at low frequencies and small at high frequencies. For steady DC current which has zero frequency, right, the capacitive reactance is infinite, which means that capacitors pass AC but block DC. Now, for example, a 1 microfarad capacitor has a reactance of 3.2 kilo ohms for a 50 Hz signal, but when the frequency is higher at 10 kHz, its reactance is only 16 ohms. As you can see, as the frequency applied to the capacitor increases, its effect is to decrease its reactance. Likewise, as the frequency across the capacitor decreases, its reactance value increases. Alright, let's move further and let's examine what inductive reactance is. So far we have looked at the behavior of inductors connected to DC supplies, and hopefully by now we know that when a DC voltage is applied across an inductor, the growth of the current through it is not instant, but is determined by the inductor's self-induced or back EMF value. Also, we saw that the inductor's current continues to rise until it reaches its maximum steady state condition after 5 time constants. The maximum current flowing through an inductive coil is limited only by the resistive part of the coil's windings in ohms, and as we know from Ohm's law, this is determined by the ratio of voltage over current. When an alternating or AC voltage is applied across an inductor, the flow of current through it behaves very differently to that of an applied DC voltage. The effect of a sinusoidal supply produces a phase difference between the voltage and the current waveforms. Now, in an AC circuit, the opposition to current flow through the coil's winding not only depends upon the inductance of the coil, but also the frequency of the AC waveform. The opposition to current flowing through a coil in an AC circuit is determined by the AC resistance, more commonly known as impedance of the circuit. But resistance is always associated with DC circuits, so to distinguish DC resistance from AC resistance, the term reactance is generally used, right? Inductive reactance, which is given the symbol XL, is the property of an AC circuit which opposes the change in the current. In other words, an inductor's electrical resistance when used in an AC circuit is called inductive reactance. Inductive reactance can be calculated using this formula here, where F is the frequency of the signal passing through the inductor and L is the inductance in henries. As you can see, inductive reactance is small at low frequencies and large at high frequencies. For steady DC signal, where the frequency is 0, the inductive reactance is also 0, which means that inductors pass DC but block high frequency AC. For example, a 1 microhenry inductor has a resistance of only 0.3 ohms for a 50 Hz signal, but when the frequency is higher at 10 kHz, its reactance is 63 ohms. We will use capacitive and inductive reactances many times in the future, but for now let's examine some use cases of impedance and let's see how this impedance can influence our circuit.